Hello everyone, welcome to my YouTube channel TechSpot. This is me, Harish Goupale. So basically in today's video, we are going to discuss about the working and functionality of SR flip-flop by using NAND gate and the RTL design implementation of SR flip-flop. Okay, you can see the block diagram of SR flip-flop on my screen. Basically, it is one of the synchronous sequential circuit which is used to store one bit of information. As name suggests, SR, it has total three inputs, that is set, reset and clock, and two outputs, that is Q and Q bar. To talk about its functionality, so it works on every positive edge of clock, means it samples data on every positive edge of clock. Below you can see the logical diagram of SR flip-flop where we have used two additional NAND gates which is connected to the SR latch, and this is how it becomes the SR flip-flop. Okay. So as we have two inputs, that is S and R, so we can have four combinations, that is 0 0 0 1 1 0 and 1 1. Let's discuss each combination to understand the whole functionality of SR flip-flop. So the first combination we are going to discuss, that is 0 and 1, where we have kept a value of S is 0 and R is 1. Beside you can see the truth table of NAND gate, which will help us to understand the functionality of this whole SR flip-flop. Okay, so as per the truth table of NAND gate, if one of the input is 0, we can predict output is 1. Okay, so here the value of S is 0 and clock is 1, so the 0 and 1 output is 1. Here clock is 1 and input R is 1, so 1 and 1 output is 0. Okay, now again, as I told you, as per the truth table of NAND gate, if one of the input is 0, we can directly predict the output is 1. So here you can see my one input is 0. I don't know the Q, because Q is the feedback. Okay, so I can directly consider the Q bar is 1. Okay, now this Q bar is going feedback for this NAND gate. So 1 and 1 output is 0. So here we got complement of Q bar, that is Q, that is 0. Q bar is 1, so complement of Q bar, that is 0. So now when my value of S is 0 and R is 1, so my flip-flop is in the reset state. Okay, now let's discuss second combination, that is the 1 and 0. So value of S is 1 and value of R is 0. Again the clock is high, so 1 S is equal to 1 and clock is equal to 1, 1 and 1, we can say the output is 0. Now for this NAND gate, clock is 1 and R is 0, so 1 and 0, I can say the output is 1. Again here for this NAND gate, my input is 0, so I can directly predict the output of Q, that is 1, as per the truth table of NAND gate. This Q is going feedback for this NAND gate, so 1 and 1, the output of Q bar is 0. Again we got the complement. So this time my flip-flop is in the set state when my value of S is equal to 1 and R is equal to 0, so my flip-flop is in the set state. Now let's discuss the third combination where my S is 1 and R is equal to 1. Okay, as the clock is also high, so as per the truth table of NAND gate, 1 and 1 output is 0. Here also for this also NAND gate, 1 and 1 output is 0. Again as per the truth table of NAND gate, if one of the input is 0, then we can directly consider output as 1. So for this NAND gate, my Q is equal to 1, and for this NAND gate also my Q bar is equal to 1. So Q bar is equal to 1 and Q is equal to 1. We can't see here the complement. Means now our flip-flop is in the invalid state because we can't see the complement between Q and Q bar. Okay. So when the value of S is equal to 1 and R is equal to 1, my flip-flop is in the invalid state. Now let's discuss the last combination where my value of S is equal to 0 and R is equal to 0. And again clock is 1. So 0 and 1, obviously output is 1. Okay, and here also my output is 1. Now here as per the truth table, I told you if one of the input is 0, then we can say the output is high, else no. So now we can't predict the output. So here boolean expressions will help us to get the output from Q and Q bar. So now for the Q, the boolean expression is Q is equal to this one and feedback is Q bar, so Q bar, and due to this not get the whole bar will come. So as per the De Morgan's theorem, okay, we can directly break the whole bar. Expression will become 1 bar plus Q bar and bar. So 1 bar means 0 plus q bar because of this bar, and one more bar is there. Okay, so bar and bar will cancel. 0 plus q is equal to q, means we are getting q out as it is. Okay, now for this q bar, the boolean expression will be 1 and q, 1 and q whole bar. Okay, again, the as per the De Morgan's theorem, this whole bar will break and the expression will become 0, means 1 bar plus q bar. So 1 bar means 0 plus q bar is equal to q bar. So we are getting as it is, q is equal to q and q bar is equal to q bar, you can see, means our flip flop is in the hold state. Okay, now we have discussed all four combinations. Now let's jump for the RTL design implementation of this SR flip flop by using system Verilog on a Viva tutorial. Hmm. So here you can see on my screen, I have already written and system Verilog code for the design implementation of SR flip flop. Okay, so let's discuss this code. Okay, here I have kept module name SR flip flop, and we are having inputs, that is clock, set, reset, and the reset here. Okay, and output, that is q and q bar. Okay, as we know, it is a sequential circuit. So in system Verilog we have sequential procedural block, that is always fm, and we know it works on every positive edge of clock. So you can see always fm at the positive edge of clock. Here I have used negative of reset, means if there is negative of reset, then our outputs will be reset. So I have assigned 0 to the outputs, else it works as per the truth table of flip flop. Okay, so now here you can see I have used a case statement. We know the functionality of case statement. What case statement tells, for every possible outputs we have to provide every possible inputs. Okay, so now let's discuss. So we know as per the truth table of SR flip flop, if the value of S and R is 0 0, then SR flip flop is in the hold state. So hold state means q will get the, means whatever the previous value of q, that will be hold. Okay, so I have assigned q to the output q and q bar to the output q bar. If the value of s is 0 and r is 1, that means our flip flop is in the reset state. So for that, what I have assigned, logically I have assigned 0 to the output q and 1 to the output q bar. If the value of s is 1 and r is 0, then my flip flop is in the set state. So for that, I have assigned directly 1 to the output q and 0 to the output q bar. Okay, and when the value of s and r both are 1 1, so we know that the SR flip flop is in the invalid state. So in this case, what I have assigned, logically I have assigned x to the output q and q bar. Okay, now when I execute this code, then it will give me this type of schematic where you can see the inputs plus r, clock, and the reset here. And it has created so many muxes because of the logic. Okay, because this is the behavioral logic, then that's why it has created so many muxes, and these are the two registers, one for q and one for the q bar. Okay, now to verify this flip flop, I have simple written a test bench code also. Let's discuss that code also, where you can see the module name is TB SR flip flop. I have taken the same inputs and outputs, that is set, reset, clock, and reset here, and output, that is q and q bar. This is the instantiation where this is the name of flip flop, SR flip flop design name, and this is the instance, due to instance. And the dot star wildcard operator is used whenever design inputs as well as test bench input outputs are same, then we can use this. Okay, and here I have toggle the clock at every 10 nanoseconds because my time scale is 1 nanosecond divided by 1 picosecond for design as well as for test bench. Okay, now inside the initial begin, you can see first I have given the reset value, that is 0, but I will see the output q and q bar should be 0 only. Okay, whatever the value of ASR, irrespective of that value, it will give the reset value. When the reset value 1, then I have given all the combinations. Okay, as when we click on the run simulation, as I have already click on the run simulation, we can have one of the waveform. So let's discuss this waveform. Okay, so here you can see that my clock is 0. That time, as I told you, it works on every positive edge of clock. So clock is 0 and reset n is also 0, but because of the clock is 0, it gives the unknown value. On the next passage of clock, if you see my reset is 0, so if reset is 0, obviously As per the behavioral logic, my output q and q bar are reset, means you can see the zero value. Here also my s and r is 0. Here my s is 1 and r is 0, but reset is 0, so output is 0. Okay, at this point, at 20 nanosecond my reset goes high, so now the functionality start. When my reset goes high, and that time my s is 0 and r is 1, means flip flop is in the reset state. So you can see output q, that is low, and q bar is also low. Okay, why? Because, sorry, but you can see my clock is 0 here. Okay, clock is 0, so we got the previous value. Okay, and it works on every positive edge of clock. So at this passage where my clock is also high, okay, and here you can see the value of s is 0, s is high, and r is 0. So now it is in a set state, so you can see the output of q is high and q bar is low. Okay, now again, on 40 nanosecond my clock is 0, so it stores the previous value, means we are getting previous value. Now at this point, again when my clock goes high, at this time you can see our input s and r is both are high. So if both are high, means it is the invalid state. Okay, so till the next process it will be invalid state. Now at this passage you can see again my value of s is high and r is 0, so the output q is high and q bar is 0. Okay, again on next passage my both s and r both are high, so the output is invalid. Okay, invalid. So basically in this video we have discussed the working and functionality of SR flip-flop and the RTL design implementation of SR flip-flop by using system Verilog. We have discussed the test bench also, we have discussed the waveform also. So if you are watching this video, then please click on the like button, and if you are you new to this YouTube channel, then please subscribe to my YouTube channel. Thank you so much.